오전 9시죠. 네, 오전 9시부터 3시간이라고 되어 있는데 3시간을 다 쓸지 아니면은 1시간 반만 쓸지는 사실 잘 모르겠습니다. 제가 보통은 스타일에 따라서 시간을 엄격하게 제한하는 스타일의 시험을 보기도 하고요. 아니면 시간을 거의 3시간을 그냥 다 주는 방식으로 하기도 하는데 아직 잘 모르겠어요. 이게 이제 첫 번째 정규 과목으로 첫 번째 하는 거라서 어떻게 작년에 있었던 시험 스타일이 궁금하시면 작년 레퍼지토리를 가서 보시면 됩니다. 혹시 여러분들이 작년 레퍼지토리를 못 보셨나요? 작년 자료들에 대한 접근을 못 하시고 계시는 건가요? 잠깐만요. 그렇다면 자,
들어가 줍니다.
네. 이거 말고 제 이름으로 되어 있는 몇 개의 레퍼지토리들이 보일 텐데 그 중에서 이거겠죠. 네, 여기 보시면 쭉 있는데 정작 그게 없군요. 시험 문제가 없군요. 알겠습니다. 찾아보고 시험 문제가 있으면 그거를 여기다 올리시면 불편하실 수 있으니까 우리 2025년 거에다 올리도록 하겠습니다. 그러면 참고를 해주시고 그렇게 하도록 하죠. 네. 또 다른 질문 있으세요? 시험이나 뭐나 괜찮습니다. 그러면 더 없으시면 네, 여기서 볼 거고요. 예, 그러니까 그때가 되면 여러분들은 이제 이렇게 좀 더 분산해서 앉으셔야겠죠. 예, 지금 그렇습니다. 다른 질문 없으시면 시작할게요. So now let's summarize our lecture contents up to now. So we have studied the property of a semiconductor charge as a function of surface potential. So I think that was already done in our second last lecture. So now we can understand the MOS equation. So as I told you several times previously, so this is corresponding to the overall bending across our entire MOS system. When gate voltage equal to flat band voltage, there is no bending. However, if we have additional voltage given by this quantity, then across MOS system we have bending. But MOS among these three components, actually this guy, metal, cannot make any kind of bending. So if we allow that kind of bending, then we must have vertical current across MOS, but this existence of oxide layer, perfect insulating layer, prevents the current conduction. So quite naturally, we can neglect the voltage across the metal part. Then the remaining part is just oxide potential and semiconductor potential. This semiconductor part is written as this number, so surface potential, and this oxide part is written as oxide potential. And key point is this guy, the surface potential, is an important quantity, and this one is treated as an unknown variable. So instead, this oxide can be expressed as in terms of semiconductor charge. Once again, this semiconductor charge can be expressed as a function of surface potential. So this MOS equation can be just regarded as one single equation for one single variable, surface potential. So now when you apply certain gate bias, this is the actual one you can control. You can control 1 volt. Yes, you can apply 1 volt, or you can apply 0.5 volt, or you can apply 0.0 volt. So you can control it, and what you want to get by solving this equation is just surface potential. Why? Once you have surface potential, it is given as a certain number from this relation Qs versus phi s. Now you can directly find out the number of electrons and holes, not actually holes, but mobile carrier density can be expressed in terms of our phi surface potential. That was all. So maybe you remember your previous homework number 1. So what was the homework? So at that time, I told you that just to change your surface potential. Then when you change your surface potential, then you of course you know it, and also you can calculate it. And Cox is a given number, flat band voltage is also given number, so you can make a table of this one, phi s and Vz, and when you have 0.1, then you will have a certain number. When you have 0.2, you will have a certain number. So once after make this table, then by inverting x and y relation, so now you can draw in this graphs. So as a function of a gate voltage, you can calculate the surface potential, and also since Q sub s semiconductor charge is a function of a surface potential, also you can draw the quantity like Qs as a function of phi s, or Qs as a function of gate voltage. You did it in your homework number 1. I'm not quite sure all of you have already done it or not, but I strongly recommend you to do this job. So anyway, I will assume that you have done it in your homework number 1, but problem is, in this case, phi s was varied, and you find a certain number. But usually what we have is, instead of this varying value, but usually we have a fixed external quantity gate voltage. So usually our aim is to find out phi s as a function of Vg directly. Then how can we solve this problem? The answer is quite simple. Just to solve our MOS equation. By solving MOS equation under a given gate voltage, then you will get this phi s. Then how can you solve? What is the actual mean to solve this problem? So here you have a linear term of phi s, and this is just a given number, and only problem occurs with this non-linear function. Q sub s is a function of phi sub s, so you have to solve a non-linear equation. So please search or investigate how can we solve a non-linear equation. So of course it cannot be solved by analytic means, so we need a computer program, but you have to study the algorithm to solve a non-linear equation. My answer is this typical algorithm is called as a Newton method, and this Newton is that famous physicist Newton. So please do your study, self-study for Newton method. In reality, we have to solve this nonlinear equation called as the MOS equation by Newton method. Then of course we can get exact value of our surface potential under a given gate voltage. But I think that this course is not for that numerical calculation, so I will just skip it. However, in reality, actually we must solve this MOS equation. Okay, are you with me? The main point of this Newton method is quite simple. Just try to guess a value phi s and check whether this is the correct solution. Obviously, in many cases, your phi s, guessed phi s, cannot be a solution. Then what you do is, okay, I understand. My guess was not correct. Then I will introduce an additional quantity to my solution variable. Then, is it correct? Once again, we will fail. And once again, we will add further. So by repeating this kind of continuous improvement, then eventually, although every time we fail to get the correct solution, yes, there is huge error, and there is still error, and once again we will have an error. However, those errors, their magnitude can be reduced and reduced and reduced. So maybe you understand the situation. So if I have to make a certain dot play, then once I just throw one arrow, then it will make this kind of a big failure. Then later I try once again, then still my result is a fail. And again, I will just adjust my practice, so it will eventually approach it to this the center point. When we hit the center point, then this is the solution. Quite similarly, this Newton method is just another way to find out the solution by iteratively providing the guess for that this MOS equation or any kind of nonlinear equation. Please do your study. This is quite important in practice in engineering, because many problems you will see in your career if you are following the engineering path, then many equations are nonlinear. Because linear equations are so simple, they can be easily solved, and engineering sense, they are not much of a practical use. But any kind of a complicated system always yields nonlinear equations, and by solving those nonlinear equations, we believe that we can understand and analyze the property of that system under our analysis or our interest. So that's the reason why solving these nonlinear equations are practically quite important. So I strongly recommend you to study this Newton method. But this is not in our regular lecture contents. Okay, so if you have any further question, then please let me know. I'll be very happy. So anyway, this is the end of our analysis on one-dimensional MOS system. Please remember or review our lecture contents up to now. After just 2 short recorded video, then we spend almost our entire lecture hours to the study of this MOS system. Now we have a certain understanding on MOS system when it is just one-dimensional. But problem is, what we use is not actually MOS capacitor. Instead, we use MOS transistors. This is a field effect transistor. It means that along its vertical direction, we have MOS. However, the practical use of this system is not along this one-dimensional way, but our current conduction occurs. Oh, sorry about that. Not this position. Our current conduction occurs along this horizontal line. So this is the difference between MOS capacitor and transistor. So we will study the transistor structure from now on. However, MOS is the very basic of understanding MOS field effect transistor. That's the reason why we have spent so many, maybe 6 lecture hours on this MOS basic system. Okay, so now you are looking at a certain device. So this is, what is this? So This is my conventional view on transistor, planar MOSFET transistor. Planar MOSFET. Of course, nowadays MOSFET is no longer look like this because state-of-the-art devices has much complicated shape. But I think that it's completely okay. Start with this planar MOSFET. If we are a device engineer, so-called device engineer, then maybe this can be a viewpoint of our understanding on transistor shape. If we are a circuit designer, actually to us, this is not the first image we will have. Instead of that, we will have this two crossing boxes. So this is the view of a circuit designer. If I ask them to please draw a circuit, then maybe they will draw in this way. This is a top view. So in our drawing and their drawing, what is the difference? So their eye is located here on top of this two-dimensional plane, and they are just watching in that direction. In that direction, they will see from top of this square, they will see this point. And as you can see, if I just change my viewpoint from here to there, then according to this layout style, then we will see the change of position from here to there. For example, if I just pinpoint the center of our transistor here, cross, then what is the point for this point? Then of course this is the point. If I make a really one-to-one correspondence, then this drawing is not that much scaled. So if I have to draw something corresponding to this guy, then I have to draw in that way. Very fat box is required because you know this is the direction for our channel direction. So we have to have a very long line, and this part is corresponding to this part, and also this part is corresponding to this part. Please understand why I'm doing this kind of not very accurate drawing for you. Is this is a three-dimensional structure. We are now living in the three-dimensional real world, physical world, but usually what we can identify or recognize is usually two-dimensional ones. So sometimes we want to make a cross section. That cross section, this cross section is done in this way. So if I am allowed to draw further a three-dimensional one, then I have to draw in that way. Say this box is the cross section shown here, and we have another direction. This is a two-dimensional one, and we have another direction. Yes, I will draw in that way. Then we can have here certain metal plate. This is corresponding to our gate. We have seen it up to now. And where can you find this gate? Here. This is corresponding to our gate part. And after that, now we can have, for example, along this direction, we can find a conventional MOS structure. This is metal. And here, almost invisible, extremely thin oxide layer can be found. And of course, below it, we will have a semiconductor part. So this is a MOS system. And what we are currently looking at this cross section is exactly corresponding to that one. Here we have M, and where can you find the oxide? So in this scale, unfortunately, it is invisible. So you can maybe see, you can see a thin line here. This is corresponding to oxide. After that, here we have a blue region that is corresponding to semiconductor. So here we have this one, and here and there we have a different color. This different color is introduced to different doping polarity. Up to now, we have just assumed that the entire semiconductor region is doped with a constant p-type doping density called as N sub A, acceptor doping. However, in this part and another part, we have a different color corresponding to the N-type dopant. So what we can expect is here we have a certain island and another island which is doped with N-type dopant. So quite obviously here we have a p-type substrate and here we have an N-type island, so they form a p-n junction. So here you can see there is a p-n junction between these two parts, and also we have a p-n junction in these two parts. So I assume that already all of you already attended the course for p-n junctions, so I don't want to repeat the part for p-n junction once again. So this is the situation. So now, so that's the reason why this cross section just looks like this. And when we have a look at the top view for this this three-dimensional structure, then we will see this kind of boxes. One box corresponding to this long box is, yes, the one corresponding to our semiconductor. Here we have a semiconductor box, and this other one, the perpendicular one, is corresponding to our gate. So please try to imagine the three-dimensional structure of your system. And my recommendation is, well, this is just a textbook drawing, so think about the end of this structure. Well, here I just draw in this way what will happen when we go to the end of this point or this three-dimensional structure. Then what will happen? Or please think about what will happen if we go to the end of this structure, end of source and drain. Then what happens? So that will be quite interesting to you. So because we are in the device course, so always to us, device is just part of silicon material. Yes, to us it is most important. However, if we consider entire circuit, actually we have to place so many devices and connect them. Then how they are connected or how they are placed, that should be considered in your study. Okay, so anyway, now I will skip that. I will skip more detailed comments on this structure. Anyway, we have a two-dimensional cross-section of a MOS transistor. So now everybody understand this is corresponding to the gate, and we have two additional contacts here and there, left and right, and they are called as sometimes one of them is called as a source and one of them is called as a drain, and their difference actually doesn't exist. In its structure itself, they are symmetric. So if we use one contact as a source, then other one is called as drain, and if we use this guy as a source and this one is just drain, then what is the actual difference? Their roles are determined by their applied voltage. In the case of N MOSFET, if we apply a certain voltage to this point and that point differently, then usually the lower one, lowly biased contact is working as the source. Okay, are you with me? So this is the way we make a differentiation between source and drain. Usually in structural sense there is no difference, at least in its intrinsic structure. Okay, so now let's have a look at the numbers here. The flat band voltage is around -1 volt, and oxide thickness is 1.2 nanometer, so 12 nanometer. And please note that this number 1.2 nanometer is the I think that the thinnest. So this is the thinnest one possible with just pure silicon dioxide. Using just a pure silicon dioxide oxide layer, we were able to scale down our oxide thickness down to 1.2 nanometer. Of course, in reality, we can reduce its thickness even further. For example, 0.5, that is possible. However, when you make such thin oxide, actually your device is no longer working as good transistor. That's the reason why people just scaled down their oxide thickness down to 1.2 nanometer. So after that, what happened? After that, they tried to even thinner oxide, but they failed. So after that, they introduced a different high K oxide here. So high K insulators were introduced in this scene. So please remember that if oxide is pure oxide is so thin like 1.2. Yes, please.
얇아지면 안 좋은 이유가 너무 얇아지면 터널링이 일어나서.
Yes, you are right. So the showstopper was the tunneling current, because you are quite right. So 1.2 nanometer, and let's say that even thinner one 1.0 nanometer. So usually what we do is, by applying high gate bias, we usually collect so many electrons underneath this structure. Yes, we have tons of electrons, and to them actually this gate is quite attractive because we have applied quite high voltage like 1 volt or 1.5, 2 volt. So to them this is very attractive, but this existence of this perfect insulator called as oxide actually prevent the movement into that gate path. Then please think about the ability to prevent its movement. Why we say that this movement from silicon to the gate part is prohibited? It is simply given as this fact. So maybe you remember. So in our previous lecture, so at the end of our previous lecture, we have thought about the quantum mechanical effect. Actually, electron cannot exist at this point because this one is regarded as a hardware. So at the time I told you the height, energetic height between silicon and oxide. What was the value? The value was 3.1 eV. And I remember that at the time it was almost about 120 times thermal energy. So because our energy scale is more or less orders of thermal energy, this 120 times of thermal energy can be regarded as infinitely high number. So that's the reason why we were able to completely separate our semiconductor region and gate region. So yes, that was the story. However, point is, this tunneling property, tunneling is really an extremely sensitive function of thickness. For example, if we have a sufficiently thick one, then electron wave function rapidly decreasing in this oxide layer, so it cannot reach at this gate part. So that was the usual case, and this is so sensitive. So for example, 10 nanometer and 20 nanometer doesn't make any difference. Already all of our electronic wave function decayed away, so there is nothing left. I mean that starting from this boundary, then there is a rapidly decreasing function of a wave function. So say here or there, that doesn't make any difference. Already all of them died. So that was the situation. But now when you go to 1.2 nanometer, now things happens. Still we have considerable amount of electronic wave function which cannot be neglected at all. So if some of our electrons are lucky enough, then they can just go across this potential barrier. Now think about this one. Here we have a clip and there is another clip and I'm here. Well, and initially the difference was 100 meter and there was a lion. Oh, how can I draw lion? Well, anyway, so it is coming and I wanted to escape from it, and I jumped and I died because I fall out. That was the situation. And now it becomes just 10 meter. Well, can I survive? No, even though I have to survive, but I said that I cannot survive. But now let's say that this difference becomes just 5 meter, 4 meter, 3 meter, 2 meter, then what will happen? Slightly changing the difference between these two clips can introduce big difference in my destiny. If it becomes just 1 meter, I'm not so sure if I can escape from here. Maybe this lion can also follow me, so I'm not that quite sure. But anyway, problem is this tunneling property is extremely dependent on the distance. So that's the reason why 1.2 was just acceptable, and if they try to reduce the thickness a little bit, then sharp increase of gate current occurs. So then why this sharp gate current is becoming a big trouble? So it is so if we have such kind of gate current, then overall our system cannot be sustained at all. So we wanted to have minimize the gate current. So gate current should not happen in any cases. So that's the reason why we just stopped here and find out different ones. Okay, that was a really good question. And then the answer is quite simple. Tunneling was the showstopper. So we have to introduce. Still, we wanted to maximize or increase oxide capacitance. However, we wanted to keep the physical thickness of our insulating layer. So what we did was, not myself, but engineers did was Cox is given as a function of permittivity of oxide layer and physical thickness of oxide layer. That was the expression for our oxide capacitance. We wanted to maximize it. However, at the same time, we wanted to keep this Tox. This is more or less the same. Then how can we increase this Cox? From this expression, it is obvious that the way we can increase Cox is increase permittivity of oxide layer. Then how can we increase the permittivity of oxide layer? Pure silicon dioxide has just 3.9 of relative permittivity. So if we just keep using the pure silicon dioxide, we cannot get higher epsilon value. So we switched into so-called high K material, and typically its permittivity value, relative permittivity value, is around 20. So depending on the situation, we have a slightly higher or slightly lower, but we have 20. So compared with this number, 3.9 was pure oxide, and now we have 20. Then what is the difference? We have 5 times the difference in the permittivity. It means that even though when we increase our oxide thickness by amount of 5 times, still we can have the same Cox value. So we have tons of rooms to further reduce the oxide thickness. So that's the reason why now we can control the gate current in a negligible level, at the same time can have high enough oxide capacitance. High K material itself is just a commodity. Everybody can use this oxide permittivity. I'm quite afraid that maybe our recording is lost. Okay, so let's cross our fingers. So I'm not quite sure. But anyway, nowadays this high K material is regarded as granted. So still we have, although we have achieved quite high Cox value, but always we wanted to get more and more. So therefore we have to reduce once again the thickness of our high K material. But point is, when you have a look at more closely this high K layer, high K dielectric layer, then it looks like this. So the entire stack cannot be high K. Why it is called as high K? We are now, although we are using epsilon, sometimes the permittivity is called as some guys K parameter. So although we say that permittivity is 3.9, but some guys say that K equal to 3.9. They are used almost with the equiprobability. So high K is, in our term, high epsilon material. Well, anyway, our stack is no longer look like this, the uniform one with high K material. More detailed one is, here we have a silicon substrate, and we have very thin layer of silicon dioxide. Usually people say that this is just one layer of silicon dioxide. Otherwise, here we have used hafnium dioxide. This is the typical high K material, and this is their mole fraction is like this. However, the attachment of our high K material onto the silicon, direct attachment, is not possible. So in order to glue them, so we need at least one single layer, and this one single layer is known to have the thickness of 0.5 nanometer. It is regarded one single layer. So it means that although we can introduce high K material, what happens? Let's assume the extreme case. If we reduce the thickness of high K material 0, infinitely thin high K layer, even though we will have a certain numbers corresponding to 0.5. Of course, if we make just 0.5 nanometer thick pure oxide, then our transistor is just to stop working, because there will be tons of gate current, so gate leakage current will just exponentially grow, so it's not possible. So it means that after using this high K material about 20 years, for 20 years quite happily, and we are at the end of once again this technological limitation. So but always they still wanted to increase this COX value. So I think that the required value, eventual technology. So when I say eventual, it's not saying 2010, 2100, not like this, but you have to live, you have to survive still in 2030, yes, and you have to survive also 2040. Around this time scale, actually we need the equivalent oxide thickness about 0.7 nanometer or even shorter. One is required. So how can you do that? I have no idea, but there are so many dedicated engineers for this gate stack. This is one of the most important building block of our transistor. So they are trying to find out a way to further scale down this effective diox. Okay. So is it enough for your question? Okay. So that was a really good question. But right now we are just talking about pure silicon dioxide. So my take-home message is, nowadays we are using high K material. However, anyway, all kinds of this gate oxide related quantity as just represented as oxide thickness. Although we have high K material, but we can convert the effective oxide thickness, effective oxide thickness from this way. We have COX, measured COX. It is just given as EOT by oxide permittivity. We say that although this high K stack is no longer made of pure silicon dioxide, but anyway, we just measure COX, and using 3.9 epsilon 0, then we extract effective equivalent oxide thickness as if it is made of pure silicon dioxide, because it is only because that is good for comparison between different technologies. Whether you have introduced high K, whether you have introduced just pure oxide, that doesn't matter. Important one is just oxide capacitance per unit area. So per unit area, it is more intuitive to talk about thickness. Let's say that if you have to always talk about farad per square centimeter, maybe that will be quite difficult to remember the numbers. Okay, I have 2.8 microfarad per square centimeter. That is quite difficult to remember, but it is corresponding to just 1.2. I wanted to have a 1.0. That is easy to remember, so that's the reason why we use effective oxide thickness. I'm not quite sure this E is corresponding to effective or equivalent, but whatever. So they are using certain converted value. Okay, and this oxide thickness is more or less corresponding to 90 nanometer technology. 90 nanometer technology means that now our transistors channel length, what is the channel length? So this is the channel length in this case. This is channel length, yes, gate length or channel length, they are not exactly equivalent, but they are in many cases used in a similar manner. So of course, right now in this diagram or cross section, I have drawn the system with 1 micrometer gate length. So this is extremely long channel, 1 micrometer. However, when you say a certain technology is 90 nanometer technology, means that we can reduce its gate length down to that number, 90 nanometer. Although we draw in this way, but using this technology, actually we can make a certain device whose gate length is 90 nanometer. So that is the meaning of this number. Simply speaking, minimum channel length or gate length. That is the meaning of this technology node number 90. Yes, that was an old-fashioned way, and nowadays everybody in this room should understand. Nowadays we are living in the era of 3 nanometer node, and it means that, can you draw the transistor whose gate length is 3 nanometer? Actually it's not. So when we had 90 nanometer technology, that was really corresponding to the exact minimum length. However, for certain how can I say, for certain more times, so people abandon that kind of naming convention. So although nowadays this is 3 nanometer, but the actual length is not 3 nanometer, is much longer, like about 15 nanometer around. So that is, then why we don't call it as a 15 nanometer technology? So there is a historic reason, because already we have used those numbers in our former technology node. So that's the reason why we cannot, if you say this technology is 15 nanometer technology, then nobody will love your technology, because they always wanted to have the shortest number or smallest number you can have. So this 3 nanometer is more or less like a advertisement or trademark. So this is the trend of industry. So just to think that this is a brand name for your technology nowadays. But previously they had the real meaning. 90 nanometer, then shortest length you can make was 90 nanometer. Okay, so now I'm saying that this is about 90 nanometer technology, but even though that is 90 nanometer technology, we are now talking about LG equal to 1 micrometer. It means that from the viewpoint of this technology, this 1 micrometer one is extremely long one, 11 times longer than its minimum channel length. So that can be regarded as a long channel MOSFET. If you make a long channel MOSFET, their IB characteristics becomes almost ideal. So we will see that one from now on. If you go to this one, this is the typical graphs you have to consider when you characterize your transistor. So if I meet some students, and please prepare IB characteristics of your transistor, sometimes they make different graphs, but most important one for characterization is actually this guy, this left one. So here you can see drain current is drawn, yes, and here x-axis is gate 1, and this actually these two graphs are identical. Data points are identical, but point is here we have introduced linear scale, and here we have introduced logarithmic scale for our drain current. So this is the right one is called as a semi-logarithmic graphs. So this is the most important one you have to have. So now you can find that there are two different curves. 1, 2. It is also important because this one is 0.05, although that is used, but there is no given value. So for example, if you like, you can use 0.01. If you like, you can use even higher values like 0.1. But anyway, point is, anyway, you have to have a low VDS condition. That is a requirement. And another one is here you have 1.1 volt, and this is a given number. This given number is corresponding to VDD. VDD means that the maximum voltage you can apply to your single transistor. So of course that is, you can actually select that number, but there is a strong recommendation for that number. For example, one foundry company sell their transistor to a certain designer, then the foundry company guys recommends that please use this transistor with 1.1 volt VDD. This transistor is made and designed for that purpose. If you apply, for example, 2 volt or 5 volt, then I cannot guarantee the correct operation of this transistor. Are you with me? So this is there exists desirable VDD value. So usually we follow that one. So anyway, we have to, in order to characterize this transistor, we have to have another graph with drain voltage equal to VDD. So now you can understand the difference between these two lines. Their difference is quite obvious. What is the difference? The difference of VDS. One is the lowly biased case, lowly drain biased case, and one is highly biased, maximally biased case. Then you can find the difference. Of course, drain is highly biased. We expect that current is higher than lowly biased one. So you can easily understand, well, the difference between these two numbers. Yes. Here we have a relatively low current, and here we have a relatively high current. Yes, why do we have a higher current? It is obvious because we are now attracting our electrons with higher magnitude. So that's the reason why we have a higher one. However, this is so let me just slow down. So this number is typically quite important. So drain current at gate is biased to VDD, and also drain is equal to VDD. It means that since you are already in the graduate school or your senior level, I just jump into the direct point. Gate voltage is used to collect our electrons, and drain voltage is just to attract or drive our electrons into the drain contact. So it means that this condition is we collect most electrons. The number of electrons we can have is maximized, and this one is corresponding to the maximum drivability. We are driving our electron, collected electrons at most. So it means that number of electrons and their driving force, both of them are maximized. So this number, this drain current is the maximum current we can expect out of this given transistor. Okay, are you with me? So this is quite important. What is the desirable number? We wanted to actually maximize it. If that number is high, then we will love it. And when this number is low, so this is not a good sign for your technology. Okay, that is one thing. Another thing is, now let's go to this low gate bias. So usually that is measured at gate voltage equal to VDD condition. But when you go to this relatively low bias case, then now you can see that two different lines. So although they look like one single line, but you can see that they are a little bit fat compared with these two ones because they are almost merged, but they are not completely identical. So there are two different lines and almost invisible or indistinguishable. So in this case, this one, let me just write down ID at gate voltage is low and drain voltage is low. That is one thing in the one in below. And another one is ID at VGS is equally low, however VDS equally biased to VDD, the maximum drivability. So in this long channel device, they are quite similar, almost indistinguishable. It means that, wow, even though we have increased the drain voltage to its maximum value, still our drain current does not increase any further. Think about this one. Now here we have a gate voltage which is lowly biased, and now we say that, oh, since this is a low gate bias, actually we have to have a very small number of electrons. So a little bit small number of electrons, and now we try to attract them by applying small or low drain bias or high drain bias. This similarity between these two graphs just shows that in this case, whether we have a VDD, whether we have a 0.01 or 0.05 volt, doesn't make any role for determining the drain current. So completely, the drain current is determined by only gate bias. Drain bias doesn't play any role. That is an important one. Once you wanted to turn the transistor off, I wanted to turn on the transistor, or I wanted to turn off the transistor, that your wheel appears not in your drain terminal, but on your gate terminal. Your gate voltage, this is your wheel to turn it on or off. So simply means that this ideal condition means that when you say off, then regardless of the second terminal's value, whether that is small, large, or VDD or 0.05, your wheel is realized and your transistor doesn't conduct any current. This is the ideal case. But unfortunately, if we go to short channel, relatively short channel transistor, not like 1 micrometer, but instead, for example, 90 nanometer technology or 90 nanometer transistor, which is the shortest one available in this one, then depending on your drain voltage, your original current can be deferred in this way. This is really a bad case. If that happens significantly, then your transistor or you cannot use this technology any further. Why? Because although you wanted to turn off your transistor, but when you apply high drain bias, then your transistor still conduct the current. So it means that your system does not work properly. You want to have zero, almost negligible current when you apply zero gate bias, but in this case you will have a significant amount of current conduction. So this is the showstopper of transistor scaling. Nowadays we means that engineers have sufficient ability to make even shorter transistor. So although we say that transistor length, channel length is nowadays 15 nanometer, 15 nanometer is not for our not determined by our fabrication property. We can make an even shorter one, 1 nanometer, 2 nanometer. Already several decades ago, people just make their champion device with just a few nanometer long channel lengths. That is possible. But point is, when you make such kind of drastically scaled down transistor, then many problems occur. But among them, the typical one is this behavior. You wanted to have zero current or quite a small current, but that current level is not solely determined by your gate voltage, but also dependent on your drain voltage. That is problem, and the shift of your curve at low drain voltage case and high drain voltage case, this difference is quite important, and we will later see how can we quantitatively specify this degree, and that is the critical number we will see. So actually almost many of our attempt to make a better transistor is related to this quantity. How can we have this so-called Dibble effect as small as possible or at under a manageable level? So let me just summarize this slide. So if we ask ourselves what are important points in this curve, then we have to answer that way. The point we have to keep in mind is, first of all, this point. This point is corresponding to the maximum current we can have. Yes. And another one is this point. Here we have a certain drain current. Now this is corresponding to drain current, but now gate voltage equal to 0 volt. 0 volt is typically used to turn off our transistor in our digital circuit, and drain voltage equal to VDD. So this is the undesirable current. If this system, this transistor is ideal, then it should be negligible. But as you can see, this is no longer negligible. Then this is orders of just 0.2 or 0.3 nano ampere for our case. And here you can see this one, this value is just 0.1 milliamp. So please try to make the difference between these two numbers. There is a 1, 2, 3, 4, 5, not 6. So about 5 orders of magnitude difference between these two numbers. Are you with me? So then my question is this enough for our working transistor or good transistor or not? It really depends on the case. It means that yes, the on current, which is the maximum current, and off current, the condition where gate bias equal to 0, it can show some differences for most scaled devices, not for this long channel device, but scaled device. If this number is corresponding to 10 to the 5, then usually we say that this is not that high. We wanted to even higher value. However, why do we have this kind of variant? In this case, on current itself is quite high. So since on current is high, we can live with it. However, we can have another one like a 10 to the 9. Yes, it is regarded as a high number. But unfortunately, if we have such kind of a huge difference between off and on current, then usually this on current itself is quite small. Why do we have this kind of a difference? Because this IV characteristics shows clear two-phase behavior. One is exponential behavior, and one is sub-exponential behavior. This is just a linear dependence on our gate voltage. So simply speaking, in order to make this high difference between our two transistors or two current level, what we can have is quite easy. So if we draw ID and VG, and if it starts from very low point and only at the end of its operational range, if we go to this way, then we will have quite a small on current but extremely low off current. This is the magic to increase on-off ratio, ion over I-off. Then we will have quite many orders of magnitude difference in our transistor. But on the other hand, if we wanted to increase this on current, then actually we have to increase the range of our strong inversion rhythm. So now we have a certain increase, but point is now we have almost a given slope here. So although we have increased a little bit, but increase of off current is really huge. So that's the reason why our on off ion over I off reduced drastically. Well, so to some of you, maybe this is a dumb way to follow, but in this case, increase of on current is not measured in a logarithmic way. In this case, on increase of on current is determined in a linear way. So 10% increase of on current, that really matters. 10% increase of your leakage current, that doesn't mean anything, because off current varies its orders of magnitude quite easily. So they are really varying. Even when you have identical devices, but they can show much differences. But on current doesn't show much variation. So increasing on current is much more precious than increasing the off current in a same amount of ratio. So that's the reason why, although we sacrifice this on and off ratio, sometimes we wanted to maximize on current. So this type of transistor is used for high performance variation of our circuit. And another one like a 10 to the 9, this one is used for our low power application. So if we wanted to have low power application, we usually wanted to use the transistor which is not that much powerful, however leakage current is extremely low. That is our choice. However, for some cases, we don't care about leakage current. We just wanted to make a powerful transistor. Then what will happen? In that case, we will use high performance transistor. Let's think about this one. You have very small devices which should be, for example, attached to your skin. Then can you use high performance variants of this technology? Obviously not. You have to have ultra low power transistor. But instead, on the other hand, you are now working with NVIDIA and you wanted to make the world most powerful system, computer system to train your next generation AI system. Then will you use low power one or high performance one? Of course, you have to use selectively high performance one for your critical circuit path. So that's the reason why we have introduced different options for our technologies. So okay, so today instead of diving into two-dimensional modeling of our MOS system, I just describe how can you see the IB characteristics. There are two types of IB characteristics. The one shown here, this is ID versus gate voltage. Typically, this one is called as input characteristics. Why? Because gate is regarded as an input terminal. And another one is this one, this ID versus drain voltage, and this one is output characteristics or output curve, because drain is regarded as drain is regarded as an output terminal. So okay, so that was up to now. All of my discussion was so qualitative. So however, later in this lecture we will go to more qualitative quantitative analysis on their properties. Okay, thank you. And if you have any question, please come to me, then I will be happy to answer your question.